and we'll keep drifting, floating together through the mysteries. 100 Big Bang mysteries, looping softly, endlessly, through the night. Tonight we'll drift through the first heartbeat of creation, so brief it almost never happened, carrying hints of a universe that came before. The cosmic background glow, a faint ancient lullaby still humming from the dawn of time, and space-time itself stretching softly outward, raising the quiet, impossible question of what waits just beyond the edge of everything. There's nothing you need to do now. Just let your body sink heavier, heavier. Feel the mattress holding you, every muscle softening, your heartbeat slowing. Thump, thump, matching the rhythm of space itself. Shoulders melting down, jaw releasing, each breath pulling you deeper, deeper into the calm, the quiet, the dark. If this helps you rest, tap subscribe, comment, and hit like, so others can find this calm too, but only if your eyes are still open. Otherwise, just drift. Now, let's drift into Big Bang. In the beginning, before beginning had meaning, there was something smaller than small, tinier than the tip of a pin, a cosmic singularity, infinitely dense, infinitely hot, all of space, all of time, all of everything, compressed into a point with no dimension, no direction, no yesterday, no tomorrow, just potential, pure potential, breathing, waiting, and your breath now, soft, shallow, matching that ancient rhythm, in, out, feeling yourself compress, condense into this moment, this bed, this darkness. Scientists call it the primeval atom. Georges Lemaitre whispered this idea first in 1931, imagining all of creation as a cosmic egg, cracking open, spilling forth reality. He saw the mathematics, the way galaxies drift apart, and traced them backward through time, through eons, until they converged, thump, thump, into a singular point of origin. Let your thoughts converge now, narrowing, focusing on the weight of your head on the pillow, the gentle pressure, pulling you down, down. Before that first moment, before the clock of time began ticking, perhaps there was quantum foam, a seething soup of possibility, where the laws of physics as we know them dissolved into something stranger, something we can barely whisper about. Planck time, the smallest possible tick of the cosmic clock, 10 to the negative 43 seconds. That's when our story can truly begin. But before that, silence, unknowable silence. Let that silence fill you now, the quiet between your heartbeats, thump, thump, the pause between breaths, and then expansion. Not an explosion outward into space, but space itself, unfurling, stretching, growing, carrying everything with it. The inflationary epoch, a fraction of a second, when the universe doubled and doubled and doubled again, faster than light, because it wasn't things moving through space, it was space itself, inflating like a balloon, smooth, endless, your chest rising now, like that cosmic inflation, slow, expanding, and falling, contracting, in perfect rhythm. This inflation, so brief, solving mysteries we hadn't even asked yet. The horizon problem. Why distant parts of the universe, parts that should never have touched, never have shared information, look so remarkably similar, so uniform, because they were once together, pressed close, sharing temperature, sharing energy, before inflation tore them apart, stretched them beyond each other's cosmic horizons. Now they're strangers, separated by the expanding gulf of space. But they remember being one, just as your body remembering how to relax, how to let go, muscle memory of sleep, ancient, instinctive. And the flatness problem, why our universe is so perfectly balanced, so geometrically flat, not curved into a sphere, not curved into a saddle, but flat, stretched flat by that incredible inflation, like pulling wrinkles from a bed sheet, smooth, even. The curvature density parameter, omega sub k, so close to zero, so precisely balanced, that we float in this flat geometry. You too, floating now in your flat bed, in your flat darkness, weightless, drifting, in those first moments when the universe was smaller than an atom, hotter than imagination. Energy and matter were indistinguishable. A quark gluon plasma, quarks swimming free, not yet bound into protons and neutrons, gluons zipping between them, carrying the strong force, everything fluid, everything connected, temperature beyond billions of degrees, where particles collide and transform, matter becoming energy, energy becoming matter, in an endless dance. Feel the fluidity now in your limbs, no longer solid, but liquid, melting into the mattress, boundaries dissolving. As the universe expanded, it cooled. Thump, thump, like a breath exhaled into winter air, and the quarks began to find each other, binding into triplets, making protons, making neutrons, the strong force pulling them together, holding them tight. This happened when the universe was perhaps a microsecond old, 1/1,000,000th of a second. And already it was growing, changing, and cooling into complexity. Your own cooling now, body temperature dropping slightly as sleep approaches, as metabolism slows. Thump, thump, slower, slower. Big Bang nucleosynthesis, the forging of the first atomic nuclei, in the first 3 minutes, 3 precious minutes, when temperatures were just right, not too hot, not too cold, protons and neutrons fused, making deuterium, making helium, a little lithium, the universe's first chemistry, 3/4 hydrogen, 1/4 helium, by mass, a ratio we still see today, written in the stars, in the gas between galaxies, in the very breath of cosmos. Breathe that ancient ratio now, 3/4 in, 1/4 out. No, just breathe, naturally, easily. No counting, no trying. But there's a puzzle, the lithium problem. We predict more lithium than we observe. Where did it go? This primordial lithium. Did stars destroy it? Did we miscalculate? Or is there something deeper? Some physics we don't yet understand, whispering to us from the first minutes of time. Puzzles are okay. Mysteries are okay. Not knowing is okay. Let the not knowing wash over you. Release the need to understand, to grasp. Just drift. Drift. For 380,000 years, the universe was opaque, a fog of plasma, photons scattering off free electrons, light trapped, unable to travel, like trying to see through a cloud, everything glowing, everything connected, no shadows, no darkness, just endless, just dazzling, fog. But you're in darkness now, blessed darkness, the darkness of rest, of safety, of sleep approaching. Then came decoupling. The moment matter and radiation parted ways. Electrons combined with nuclei, forming the first neutral atoms, mostly hydrogen, and suddenly photons were free to travel. The universe became transparent, and light, ancient light, began its journey. That light is still traveling, stretched by expansion, cooled from visible fire to microwave whisper, the cosmic microwave background, a baby picture of the universe, showing us how it looked, smooth, nearly uniform, with the tiniest ripples, seeds of everything to come. Those ripples, quantum fluctuations from inflation, stretched to cosmic size, tiny differences in density. Some regions slightly denser, some slightly less. And gravity, patient gravity, and began to amplify them. Dense regions pulling matter inward, thump, thump, like your heart pulling blood, rhythmic, persistent, growing denser, growing stronger, until the first stars forming in the darkness, the cosmic dark ages ending, 300 million years after the beginning, maybe 400 million, clouds of hydrogen, collapsing under their own weight, compressing, heating, until nuclear fusion ignited in their cores, and they shone, the first stars, massive, bright, burning hot and fast. Population 3 stars, made only of primordial hydrogen and helium, no heavier elements yet, no carbon, no oxygen, no iron, just the pure ingredients from the Big Bang, burning, fusing, creating the first heavy elements in their cores. These first stars, they died young, exploding as supernovae, scattering their new elements, carbon, oxygen, nitrogen, into space, enriching the universe, making future stars, making planets, making life possible. You are made of star stuff, Carl Sagan whispered, and he was right. The iron in your blood, the calcium in your bones, forged in stellar cores, billions of years ago. You are ancient. You are cosmic. You are drifting. And as stars formed, they gathered, drawn by dark matter's gentle pull. Dark matter, the invisible scaffolding, 5 times more abundant than ordinary matter. We cannot see it, cannot touch it, but we feel its gravity, bending light, holding galaxies together. It was there from the beginning, perhaps WIMPs, weakly interacting massive particles, perhaps sterile neutrinos, perhaps something stranger, drifting through space, through stars, through planets, through you, right now, invisible, unfelt, but present, always present. Dark matter formed halos, invisible wombs where galaxies could birth. Its gravity pulled normal matter inward, gas falling, swirling, forming disks, forming spirals, forming ellipticals. The first galaxies, small, irregular, chaotic, they merged, combined, grew, building bigger galaxies like the Milky Way, like Andromeda. Beautiful islands of stars, hundreds of billions of stars each, floating in the dark matter sea, and your thoughts like galaxies, distant, separate, slowly merging into the unified darkness of sleep. The cosmic web began to emerge, filaments of galaxies, strung like pearls on dark matter threads, connecting clusters, connecting superclusters, and between them, voids, vast empty spaces where few galaxies dwell. The universe is not uniform, but structured, like a sponge, like foam, like neural networks, patterns repeating at every scale. Your own neural network, quieting now, connections dimming, thoughts scattering, dispersing into void. Baryon acoustic oscillations, sound waves in the early plasma, frozen into the distribution of galaxies, a cosmic ruler, showing us how far pressure waves could travel before decoupling, before the fog cleared. We measure this, and it tells us about dark energy, about the composition of cosmos, about how fast space is stretching, carrying galaxies apart, your own oscillations, your breathing, your heartbeat, thump, thump, slowing, deepening, becoming the only rhythm that matters. After the first stars came reionization, their ultraviolet light, so energetic, splitting hydrogen atoms back into protons and electrons, turning neutral gas back into plasma, in bubbles around each star. Bubbles growing, touching, merging, until the entire universe was reionized, transparent in a new way. This happened gradually, over hundreds of millions of years, a slow dawn, washing across creation. And your own dawn is hours away, hours of rest, of darkness, of restoration ahead. Photons, everywhere photons. In the early universe, the photon epoch, radiation dominated over matter. There were billions of photons for every baryon, every proton and neutron. That ratio remains. The universe is full of relic photons from the CMB, from starlight, from everywhere, washing over us, through us, unnoticed, like sleep washing over you. Inevitable, natural. You don't have to invite it, just allow it. Cosmic neutrinos, even more elusive than photons, created in the first second when the universe was hot enough for weak interactions to transform particles freely. These neutrinos decoupled early, when the universe was just 1 second old. They've been free streaming ever since, passing through everything, a cosmic neutrino background, colder even than the microwave background. We've never detected it, but it must be there, a whisper beneath a whisper, like the quiet beneath your thoughts, the stillness beneath sensation, always there, waiting. The universe has a thermal history, a story of cooling. In the beginning, all forces were one, unified. As it cooled, forces separated. First gravity, pulling away at the Planck scale. Then the strong force, separating at the grand unification epoch, when the universe was 10 to the negative 35 seconds old, leaving electroweak force, which itself split into electromagnetism and weak force at electroweak symmetry breaking, when the universe was a picosecond old, each transition a cosmic phase change, like water freezing, suddenly, completely, changing the rules, changing reality. These phase transitions, they may have created topological defects, cosmic strings, domain walls, monopoles, exotic structures, predicted by theory, perhaps scattered through space, perhaps long decayed. We search for them in the polarization of the CMB, in gravitational wave signals, in the distribution of galaxies, searching, always searching for evidence of the universe's violent youth. But you're not searching now, you're releasing, letting go, allowing the search to end. For tonight, matter and antimatter, born equally in the Big Bang, every particle with its antiparticle, but they annihilate on contact, releasing energy. And yet, we exist. We are made of matter. Where did all the antimatter go? Leptogenesis, perhaps, or baryogenesis, processes in the first second that created a tinier symmetry, one extra matter particle for every billion matter-antimatter pairs. And when the rest annihilated, that tiny excess remained, became stars, became planets, became you, one in a billion, surviving, persisting, like your consciousness, that tiny flame, flickering, dimming, soon to rest. Friedman equations, derived by Alexander Friedman, describing how the universe expands, relating the expansion rate, the Hubble parameter, to the density of everything, matter, radiation, dark energy, curvature. These equations, they tell us the universe's fate, whether it will expand forever or collapse back. They use the density parameter, omega, comparing actual density to critical density, the threshold between eternal expansion and eventual collapse. Our universe, it seems, is right at critical, flat, balanced on a knife's edge, expanding forever, but ever more slowly. Or perhaps not, because there's dark energy, discovered in 1998, when astronomers measured distant supernovae, standard candles, and found them dimmer than expected, farther than expected. The universe's expansion, accelerating, not slowing as gravity should dictate, but speeding up. Something, some energy, fills empty space, pushing space apart. We call it the cosmological constant, lambda, Einstein's old friend, the term he called his greatest blunder. But perhaps it was his greatest insight. Empty space has energy, has pressure, negative pressure, pushing outward, dominant now, shaping the universe's future. 3/4 of the universe is dark energy, less than a quarter dark matter. About 5% normal matter, atoms, stars, planets. We are the minority, living in a cosmos we barely understand, shaped by forces we cannot see, like sleeping, entering a realm we don't control, don't fully understand, but trust, must trust, because we've done it 1,000 times and awakened whole. The equation of state, relating pressure to density. For matter, U equals 0, no pressure. For radiation, U equals 1/3. For dark energy, if it's truly a cosmological constant, equals -1, negative pressure, pushing space apart. But perhaps W is different. Perhaps it changes. Early dark energy models, phantom energy, quintessence, fields that evolve, that shift, changing the universe's fate, changing everything. If W is more negative than -1, phantom energy, the universe ends in a big rip, expansion accelerating, faster, faster, until space tears apart. First galaxy clusters, then galaxies, then stars, then planets, then atoms. Everything ripped to shreds in perhaps 20 billion years. But if U is -1 exactly, heat death, the universe expanding, cooling, forever, stars burning out, black holes evaporating, until nothing remains but thin soup of particles, cold, dark, entropic, in 10 to the 100 years, or more. Either way, so far, so impossibly far, that tonight, tomorrow, your lifetime remains precious, remains real. But let's not drift to endings, not yet. There's so much more to whisper about. The Lambda CDM model, our standard model of cosmology. Lambda for dark energy, CDM for cold dark matter. Cold meaning slow moving, not hot, not zipping around at nearly light speed, but sluggish, allowing structure to form. This model, it fits observations beautifully. The CMB, galaxy distributions, supernova distances, all fitting, all consistent, with 6 parameters, just 6 numbers, describing everything. The age of the universe, 13.8 billion years. The Hubble constant, how fast space expands, about 70 kilometers per second per megaparsec, meaning galaxies 1 megaparsec apart drift apart at 70 kilometers per second. Farther galaxies, faster, linearly. Hubble's law, the whisper of expansion, cosmic redshift, light stretched, reddened by the growth of space itself. Your body stretching now, not literally, but sensation stretching, time stretching, each moment becoming elastic, soft, longer than the last. Thump, thump, seconds feeling like minutes. Minutes dissolving into the eternal present. You might notice how heavy your eyelids have become, how far away sounds seem, how little you care about staying awake. It's okay. It's more than okay. This is exactly where you should be. The observable universe has a horizon. Not because space ends, but because light from farther away hasn't had time to reach us. The universe is 13.8 billion years old. But because space expanded, the horizon is 46 billion light years away, in all directions, making the observable universe 93 billion light years across. Beyond that, more universe, probably infinite universe, forever, but forever invisible, beyond the light horizon, beyond causality, forever unknown. Let the unknown be unknown. Release the need to see beyond, to understand beyond. Just be here, in this small sphere, this bed, this body, this moment. Structure in the universe. It grew from quantum seeds, tiny fluctuations in the inflation field, stretched to cosmic size, giving different regions slightly different densities, and gravity, working on those seeds, pulled matter into the regions that were slightly denser, making them denser still through gravitational instability, the Jeans instability, named after Sir James Jeans. When a region becomes dense enough, its own gravity overcomes pressure, and it collapses, forming stars, forming galaxies, forming clusters. Everything we see, everything, grew from quantum uncertainty, from the universe's inability to decide exactly how to begin, and from that uncertainty, beauty, structure, life emerges. The power spectrum of the CMB, showing us those initial fluctuations, plotting temperature variations against angular scale. It has peaks, acoustic peaks, from sound waves in the plasma, waves that compressed and rarefied the gas. The first peak, at about 1 degree, tells us the universe is flat. The second peak, the third peak, they tell us about dark matter, about baryons, about the composition of everything, written in the sky, in microwave whispers, a cosmic code waiting to be read. And maybe that's what consciousness is, the universe reading itself, noticing itself. And you're the universe, noticing what it feels like to drift towards sleep. The Sachs-Wolf effect, photons climbing out of gravitational wells, losing energy, appearing cooler in the CMB. The integrated Sachs-Wolf effect, photons passing through evolving structures, gaining or losing energy, as dark energy changes the depth of gravitational wells. These effects, they create patterns, cold spots, hot spots in the cosmic background, telling us about dark energy's history, about how structure grew, all of it recorded, all of it preserved in that ancient light from 380,000 years after the beginning, the Sunyav-Zeldovich effect, where galaxy clusters scatter CMB photons, shifting their frequency. This tells us about the hot gas in clusters, about cluster distances, independent of redshift, a cosmic ruler, another tool for measuring the universe, for weighing dark energy. And all these tools, all these methods, they agree. They tell the same story. The universe emerged from a hot, dense state, expanded, cooled, formed stars, formed galaxies, and now accelerates apart and will continue for eons, for eternity. Perhaps, but not tonight. Tonight you're still, centered, here. Gravitational lensing, mass-bending light, predicted by Einstein, confirmed in 1919 during a solar eclipse, and now we see it everywhere. Galaxies lensing background galaxies, dark matter halos, lensing distant quasars, even the CMB, weakly lensed by foreground structures. The patterns it creates, they tell us about mass distribution, dark matter distribution, about everything between us and that ancient light. Seeing through gravity, seeing the invisible, made visible through its effects, like sleep's approach. You can't see it, but you feel its effect, pulling at consciousness, bending awareness, until primordial gravitational waves, ripples in space-time itself, created during inflation. We search for them in the polarization of the CMB, B modes, the telltale spiral pattern they would create, found, maybe, hints, controversies. The bicep 2 result, excitement, then doubt, dust, galactic dust, mimicking the signal. We're still searching, still listening to the vibrations of creation, gravitational waves. They've been detected from merging black holes, from merging neutron stars, LIGO, Virgo, hearing the universe, but primordial waves from inflation itself. They remain whispers beneath noise, maybe. The stochastic gravitational wave background, a hum pervading space from countless sources, primordial waves, cosmic strings, phase transitions in the early universe, bubble collisions, all contributing just to a background chorus. We listen with pulsar timing arrays, watching pulsars, nature's perfect clocks, looking for coordinated variations in their timing, signs of space-time rippling between us and them. And maybe we've heard it, maybe the data suggests something, a background detected, perhaps in 2023. Scientists still analyzing, still confirming, the universe humming, always humming, like the hum of blood in your ears when everything else is quiet. Thump, thump, the sound of being alive. Axions, hypothetical particles, proposed to solve problems in particle physics, but also possible dark matter candidates, light, ghostly, filling space, oscillating in cosmic magnetic fields, creating tiny signals we might detect. Axion cosmology, exploring how these particles, if they exist, shaped the early universe, how they cluster, how they behave, different from WIMPs, different from sterile neutrinos. Another possibility, another whisper of the invisible. The universe offers us mysteries, not to frustrate, but to invite, to welcome us into deeper looking. But tonight, no more looking. Tonight, closing, softening, releasing. 21 centimeter cosmology, using hydrogen's signature wavelength to map the dark ages, the time before first stars, when the universe was neutral, dark, hydrogen everywhere, not yet ionized. This signal, redshifted now, stretched to meters, to tens of meters, wavelength. We build radio telescopes, arrays of antennas, listening to those ancient whispers, trying to map how the first stars turned on, how bubbles of ionization grew, merged, flooded the universe with light, the cosmic dawn, happening gradually across hundreds of millions of years, like your personal dawn, still hours away, protected by darkness, by rest. Neutrinos, they free stream, meaning once they decouple, they travel unimpeded, not colliding, not interacting, just drifting. This affects structure formation because neutrinos smooth out small-scale density fluctuations. They were moving too fast to collect in small halos. Only later, as the universe expanded, did they slow enough to contribute to gravity's pull. Their mass, tiny but not zero, affects the growth of structure, affects the universe's evolution. We weigh neutrinos by studying galaxies, by studying the CMB, by seeing how structure grows differently when neutrinos have mass versus massless. The universe transitioned from radiation-dominated to matter-dominated. This happened about 50,000 years after the Big Bang. Before that, radiation, photons and neutrinos dominated the energy density, dictated expansion. After that, matter, both dark and ordinary, took control, gravity working differently, pulling structure together more efficiently. This transition, it left marks in the CMB, in how galaxies cluster, telling us when it happened and what the universe contained. Early universe, so many particles created and destroyed in thermal equilibrium. As the universe cooled, particles froze out, their creation rate fell below expansion rate, and their abundance fixed, locked in, relic density. Dark matter froze out, perhaps when the universe was a microsecond old, a nanosecond old, depending on its mass, its interactions, leaving the density we observe today. Neutrinos froze out at 1 second, their abundance predicted, confirmed by Big Bang nucleosynthesis, by the CMB, everything connected, everything consistent, one story, told in many voices. The GZK cutoff for ultra-high energy cosmic rays, protons so energetic, they collide with CMB photons, creating particles, losing energy. This means cosmic rays above a certain energy cannot travel far. They're absorbed by the CMB within about 50 megaparsecs. This cutoff, predicted in 1966 by Griesen, Zatsepin and Kuzmin, it's observed mostly, though there are hints of particles beyond it. Mysteries, always mysteries, inviting us deeper. The dipole anisotropy of the CMB, we see it slightly hotter in one direction, slightly cooler in the opposite direction. This is because we're moving our solar system, our galaxy, moving through space about 600 kilometers per second toward the constellation Hydra, toward something called the Great Attractor, a concentration of mass pulling us, pulling our local group, pulling thousands of galaxies, something huge behind the zone of avoidance where the Milky Way's dust blocks our view. We're being pulled. Everything's being pulled by local mass concentrations, by peculiar velocities, deviations from pure Hubble flow. The universe is not just expanding, it's flowing, swirling on local scales, like your thoughts, flowing, swirling, slowing into the drift, adiabatic fluctuations in the early universe, where all components, matter, radiation, dark matter, fluctuated together in the same phase. This is what inflation predicts and what we observe. But there could have been isocurvature fluctuations, where different components fluctuated out of phase. These would create different patterns in this CMB in galaxy clustering. We search for them, find none, or almost none, confirming inflation's prediction. The universe, following rules, even in its birth, eternal inflation. The idea that inflation, once it starts, never completely ends. In some regions, it stops, creating pocket universes like ours. But in other regions, it continues, inflating, spawning more pockets, more universes, forever. An infinite multiverse of bubble universes, each with potentially different physics, different constants, different everything. We'd be in one bubble, unable to see, unable to touch the others, separated by eternally inflating space. This is speculation, untestable, maybe, but it emerges naturally from inflation theory, from the mathematics, whispering possibilities, endless possibilities, bubble collisions. If eternal inflation is true, if our universe is one bubble among many, perhaps bubbles collided before our inflation ended. This would leave a mark, a cold or hot spot in the CMB, a breaking of symmetry in one direction. We look, we search. Some claim to see patterns, others disagree. Controversy, as always, at the edges of knowledge. But that's okay. Uncertainty at the frontier is where science lives, is where wonder lives. And you live in certainty, in the certainty of this moment, this darkness, this rest, cosmological redshift, light stretched by expansion, different from Doppler shift, though they look similar. This is space itself, growing, carrying galaxies apart, stretching wavelengths, shifting light toward red, toward infrared, toward radio waves. The farther away, the more redshift, the faster recession, more redshift. Hubble's law connects them linearly for nearby galaxies, but at great distances, the relationship curves, affected by dark energy, by how expansion has changed over cosmic time. We measure distances with standard candles, objects of known luminosity like Typeia supernovae or Cepheids variables, and standard rulers, objects of known size like baryon acoustic oscillation or galaxy clusters. Luminosity distance relates apparent brightness to true brightness. Angular diameter distance relates apparent size to true size. In an expanding universe, these distances just differ. They're not the same as they would be in static space. Another sign, another confirmation that space is dynamic, living, growing. The deceleration parameter, Q sub 0, tells us if expansion is slowing or speeding, negative Q, acceleration, positive Q, deceleration. For most of cosmic history, Q was positive, gravity winning, slowing expansion. But about 5 billion years ago, dark energy took over. Q went negative. Expansion began accelerating, and will accelerate forever. Perhaps the universe entering a dark energy dominated era. Now, right now, in cosmic history, and you're entering a sleep dominated era, consciousness fading, dreams approaching, perhaps curvature, the shape of space, positive curvature, a closed universe like a sphere, finite but unbounded, negative curvature, an open universe like a saddle, infinite, flat curvature, zero curvature, also infinite, perfectly balanced. The curvature density parameter, omega sub k, measures this. A universe, omega sub k equals 0, within measurement error. Space is flat, stretched flat by inflation. This means if you travelled far enough, in a straight line, you'd never return. Space goes on forever. Parallel lines stay parallel forever. The familiar geometry of Euclid on cosmic scales. The observable universe has structure. The cosmic web, filaments and voids, superclusters, clusters of clusters, like the Virgo supercluster, our address, or the much larger Laniakea supercluster, Hawaiian for immeasurable heaven, 100,000 galaxies pulled together by gravity, by dark matter flowing toward the great attractor, and voids, vast empties, like the Bhuta's void, 330 million light years across, containing few galaxies. Supervoids, regions where dark energy might dominate even more, creating cold spots in the CMB. Possibly, the cosmic web formed from those tiny quantum fluctuations. Dark matter collected first along filaments into halos, then normal matter falling in, forming galaxies in the densest nodes where filaments meet. This is structure formation, gravitational instability, collapse, cooling, star formation. All from those tiny seeds, amplified by time, by gravity, by the patient accumulation of mass attracting mass, like sleep accumulating, yes, in your body, hour by hour, deepening, deepening, until thought becomes dream, becomes nothing. Void boundaries are sculpted by expansion, by gravity's pull, draining matter from voids into filaments. The universe empties here, fills there, creating the foam-like structure we observe. Galaxies in voids, they're different, often isolated, evolving slowly. Galaxies in clusters, crowded, colliding, merging, transforming. Environment matters in the cosmos as it matters in life. But here, in bed, in darkness, environment is perfect for rest, for restoration. Hidden sector particles in the early universe, particles that barely interact with normal matter, only through gravity or extremely weak forces. Dark matter might be a hidden sector, an entire shadow physics parallel to ours, undetectable, except by gravity. These particles, if they exist, were created in the Big Bang, exist now, passing through us, unnoticed. A universe within the universe, invisible, untouchable, forever separate, except for the gentle tug of gravity, binding everything, binding you to this bed, to this earth, pulling you down, down, heavier, heavier. Pre-inflation quantum states, before inflation began. What was the universe's quantum state? Was it in the ground state, the vacuum, or in an excited state, full of energy, about to inflate? This affects predictions, affects what we should see in the CMB, in gravitational waves. The Hartle-Hawking no-boundary proposal suggests the universe emerged from nothing in a quantum tunneling event. Time itself beginning not from a singularity, but from quantum foam, smoothly, naturally. Or perhaps there was something before, another universe, collapsing, bouncing into ours. Ekpyrotic models, cyclic models, where Big Bangs repeat forever, endless cycles of expansion and contraction. String gas cosmology, from string theory, imagines the early universe as a gas of strings, vibrating, wrapping around extra dimensions. As the universe expanded, some dimensions grew large, the three we live in. Others remained tiny, curled up, Planck scale. The strings collided, annihilated, decayed, leaving particles, leaving energy, leaving the hot dense state from which our universe emerged. This is speculation, mathematics, beauty, perhaps, but we don't know. String theory remains unproven, elegant, but silent on experimental tests. The Planck era, the first 10 to the negative 43 seconds, is mystery. Quantum mechanics and gravity both dominate. They must merge into quantum gravity, but we don't have that theory. General relativity breaks down at the singularity, at infinite density. Physics as we know it stops. We need new physics, new mathematics, new ideas to describe that moment, that emergence, that beginning. But we can't test it, can't observe it, can only speculate, calculate, dream like you, drifting beyond the testable, beyond memory, into the quantum foam of dreams, leptogenesis, creating the matter-antimatter asymmetry through lepton interactions, heavy right-handed neutrinos, decaying, preferring leptons over antileptons, slightly. This created a net lepton number, which later, through Sphaleron processes, converted to net baryon number, and thus matter survived, and we exist. One possible pathway among many, explaining why the universe is not 50% matter, 50% antimatter annihilating eternally, but instead is almost entirely matter, with antimatter rare, fleeting, created in collisions, in cosmic rays, but not primordial, not abundant. Cosmic strings, if they exist, are topological defects, lines of trapped energy from phase transitions, They'd be incredibly thin, Planck scale width, but incredibly dense, stretching across the universe, perhaps forming loops, oscillating, emitting gravitational waves. We search for them in CMB polarization, in pulsar timing, in gravitational wave detectors. No clear detection, yet limits tightening. Perhaps they don't exist. Perhaps they decayed long ago or never formed, but they remain possible, theoretically allowed, waiting in the shadows of maybe domain walls, another type of defect, two-dimensional surfaces where different vacuum states meet, like cosmic strings, but walls, planes. They dominate the universe. If they were stable, overweighting everything, pulling everything into chaos. So either they're not stable, they decayed, they annihilated, or they never formed, or our theories need adjustment. Physics is full of predictions, some realized, some not, and that's okay. That's how we learn what's real and what's just mathematics, dreaming. Primordial black holes formed in the early universe from overdense regions, collapsing directly without becoming stars first. These would be small, maybe asteroid mass, maybe mountain mass, maybe larger. They could constitute some or all of dark matter. We search for them through gravitational lensing, through the gravitational waves they'd emit when they merge. Some candidate events, maybe. Or maybe primordial black holes are rare or don't exist. Another possibility among many. The age of the universe, 13.8 billion years. We calculate this from expansion rate, from the CMB, from the oldest stars, from radioactive dating of meteorites. All methods agree within error. The universe has a birthday, a beginning, and it's aged gracefully, cooling, complexifying, life arising, at least once, on a pale blue dot, orbiting a medium star in an ordinary galaxy. In all that vastness, in all that time, we exist, briefly, improbably, miraculously, and tonight you rest in that miracle, held by gravity, warmed by starlight, stored in ancient atoms from an ancient explosion that continues, the cosmic opacity barrier before recombination. The universe was opaque. We cannot see directly farther back than 380,000 years. The CMB is our horizon in light, but gravitational waves can pass through. Neutrinos can pass through. In principle, we could detect primordial gravitational waves from inflation, primordial neutrinos from the first second, seeing, feeling, back to the very beginning. But we haven't, not yet, our instruments, not yet sensitive enough. But someday, maybe, we'll hear the first moment itself. The anthropic principle observes that the universe must be compatible with our existence. We're here, so conditions allowed for galaxies, stars, planets, chemistry, life. The weak anthropic principle just says, we observe a universe compatible with observers because Obviously, the strong anthropic principle suggests the universe is fine-tuned for life. The constants of physics, just right, change them slightly, and stars don't form, or atoms don't form, or chemistry is impossible. Is this design? Is this luck? Or is this one universe among infinite others in a multiverse, most unable to create observers, but some, like ours, just right, and we exist in a compatible one because we must. The steady state theory, proposed by Hoyle, Bondi, and Gould in 1948, suggested the universe is eternal, unchanging on large scales, always expanding, but new matter, continuously created, maintaining constant density, no Big Bang, no beginning, an elegant idea, philosophically appealing, but observations killed it. The CMB, discovered in 1965, showed the universe was hotter, denser in the past. Galaxy evolution showed the universe changes, quasars, abundant long ago, rare today. The steady state could not explain, and faded into history, a beautiful idea disproven. This is science, testing, learning, correcting. Horizons in cosmology mark limits. The particle horizon, how far light could have travelled since the Big Bang, defines the observable universe. The event horizon, more subtle, marks the farthest events we will ever see, even if we wait forever, even as light reaches us from farther and farther. There's a limit. Events beyond will never affect us, because space expands faster than light, separating us eternally in a dark energy-dominated universe. This horizon is finite. There are galaxies we see now whose future we'll never see. Already, they're slipping beyond the horizon, dimming, redshifting, fading into cosmic isolation. But that's okay. We have each other here, now, on this pale blue dot, sharing this moment. Magnetic fields in the early universe might have been seeded by phase transitions, by turbulence in the plasma, by battery mechanisms creating tiny seed fields. These grew through dynamos, in galaxies, in clusters, amplifying, organizing. We observe magnetic fields everywhere, in galaxies, in galaxy clusters, even in intergalactic space, possibly primordial magnetism or generated later. We're still learning, still measuring, still wondering. The universe surprises, always. Plasma turbulence in the early universe, from inflation, from phase transitions, would create chaotic flows, eddies, vortices in the hot plasma, energy cascading from large scales to small, dissipating, heating. This turbulence might affect structure formation, might seed magnetic fields, might create non-Gaussian features. In the CMB, we find mostly Gaussian, mostly smooth, but hints, tiny hints of something more, something complex, hiding in the data. Cosmic shear, gravitational lensing of distant galaxies by foreground matter distorts their shapes slightly. We measure these distortions, map dark matter statistically. Weak lensing because it's subtle, statistical, not obvious, like strong lensing, where galaxies are clearly multiply imaged, Einstein rings. But weak lensing tells us about all mass between us and distant galaxies, dark and luminous, a cosmic tomography, slicing the universe, mapping how structure grew, how dark energy influenced that growth. Vacuum energy fluctuations, even empty space, is not empty. Quantum fields fluctuate, creating and destroying virtual particles. This gives vacuum energy, the cosmological constant. Perhaps, but we calculate vacuum energy from quantum field theory and get a number vastly larger, 10 to the 120 times larger than observed dark energy. The worst prediction in physics. The cosmological constant problem. Why is vacuum energy so small, so precisely balanced against gravity that the universe can form structure, can exist at all? We don't know. It's a crisis or a clue, pointing to new physics beyond the standard model, beyond general relativity, beyond what we understand. Protogalactic clouds collapsing in dark matter halos, cooling, fragmenting. The first generation of galaxy formation, chaotic, violent, small galaxies merging hierarchically, building bigger ones, feedback from supernovae, from black holes, regulating, pushing gas out, stopping star formation temporarily, then gas falling back, stars forming again, cycles of activity and quiescence. This is how galaxies grew, how they evolved from small to large, from irregular to spiral and elliptical, over billions of years. Patient processes working, the subtle drift of fundamental constants. Are the constants truly constant, or do they change over cosmic time? We measure carefully, looking at distant quasars, at spectral lines from billions of years ago, comparing to laboratory value today. Most measurements show no change, but some hint at tiny drifts in the fine structure constant, controversial, debated. If real, it would revolutionize physics, constants, evolving with the universe, but probably they're constant as far as we can tell, and deeper still into the mathematics, into the formalism that describes all of this. The scale factor, A of t, a simple function describing how space grows at the Big Bang that equals 0 today by convention. A equals 1 in the future, a grows forever. Perhaps this single function as contains the universe's expansion history, its derivative tells us expansion rate, its second derivative tells us acceleration. Everything encoded in this curve, this growth, this patient unfolding, like you're breathing, expanding, contracting, following its own scale factor, rising, falling, naturally, Cosmic time, the time we experience, tick, tock, forward, always forward, but there's another time, conformal time, a mathematical construct where light rays become straight lines, easier to calculate. It's related to cosmic time by the scale factor, stretching and compressing, making geometry simpler, making calculations tractable. Both times, both coordinates, describing the same universe, the same events, just different perspectives, like how you can measure your day in hours or heartbeats. Thump, thump, same day, different counting. Comoving coordinates, they expand with space, a galaxy, sitting still in comoving coordinates, even as it recedes from us in physical coordinates. This separation helps us distinguish motion through space from motion of space. Comoving distance stays constant for objects moving with Hubble flow. Physical distance grows with the scale factor. Multiply them and you convert one to the other. Simple, elegant, like your body, comoving with Earth. As Earth moves through space, you feel still, but you're traveling thousands of kilometers per second through the cosmos, orbiting, rotating, drifting, unnoticed. The particle horizon marks how far light could have traveled since the Big Bang, reaching us. It defines the observable universe, what we can see, what can affect us. But there's another horizon, the future horizon, marking events we will ever see, even waiting forever, in a universe with dark energy, accelerating. These differ. The future horizon is smaller, finite. Some events happening now, beyond it, will never reach us. They're light, fighting against expansion, losing, fading, disappearing, beyond reach, forever. Let them go. What's beyond is beyond. Rest here, in what's knowable, in what's present. The Hubble horizon is different still. It's the distance, where recession velocity equals light speed. Objects beyond it recede faster than light, but we can still see them if their light was emitted when they were closer. The Hubble horizon marks causal structure in a different way. Regions within it can exchange information. Currently, regions beyond cannot. Currently. But this changes as the universe evolves. Horizons shift, grow, or shrink, depending on acceleration. Nothing stays the same. Everything flows, changes, like consciousness, flowing now towards sleep, beyond the horizon of waking awareness. During inflation, space expanded faster than light, exponentially. Super Hubble modes were created, quantum fluctuations stretched beyond the Hubble horizon, frozen, unable to oscillate. These became the seeds of cosmic structure. As inflation ended and expansion slowed, these modes re-entered the horizon, becoming density fluctuations, sound waves, galaxies. Eventually, everything we see came from Super Hubble modes, from quantum whispers, stretched to cosmic scales then falling back into causality, patience, cosmic patience, creating everything. Curvature perturbations, described by zeta, z, the gauge invariant measure of density fluctuations on super Hubble scales. This formalism, elegant, powerful, tells us how fluctuations evolved from inflation through radiation era to matter era, conserved on large scales, growing on small scales. Zeta, nearly scale invariant, meaning similar amplitude at all scales. Almost. This is inflation's prediction, confirmed by observations. The tilt, the spectral index, slightly less than 1, tells us inflation was not exactly exponential, but close, so close. The tensor to scalar ratio, R, compares gravitational waves to density fluctuations from inflation. Large R means strong gravitational waves detectable in B-mode polarization. Smaller R means weak waves, harder to find. Current limits are less than 0.036 at certain scales. Still room for detection, still hope. Experiments running, searching, listening for those primordial ripples in space-time itself. Each measurement tightening limits, narrowing possibilities, approaching truth, or approaching the realization that R is too small to ever detect. Another mystery, quiet, subtle, hiding. Non-Gaussianity, measuring deviations from perfect randomness and primordial fluctuations, FNL, GNL, parameters, quantifying how much 3-point, 4-point correlations exceed what random Gaussian fields would give. Simple inflation models predict nearly Gaussian, FNL near zero, but alternatives, multi-field inflation, non-standard scenarios could produce large non-Gaussianity, detectable in the CMB in galaxy clustering. We measure, find FNL, consistent with zero, within errors, but still, we search for any deviation, any signal of something more complex in the beginning, just as you search softly for sleep signal in the noise of waking thoughts, waiting, quieting, releasing. Isocurvature perturbations, where different components fluctuate differently, out of phase, unlike adiabatic modes, where everything fluctuates together. These would create different patterns in the CMB at small scales. We constrain them, find mostly adiabatic, but allow some mixture, perhaps 10% or less. Another confirmation of simple inflation, which predict purely adiabatic. Simplicity emerging from observations, the universe, following the simplest path, perhaps, or perhaps hiding complexity beneath measurement precision, waiting for better instruments, better eyes, cosmic variance, the unavoidable uncertainty. We have only one universe, one sky, one CMB to observe. At large scales, few independent samples, few modes to average over. So uncertainty, irreducible, no matter how perfect our instruments. We cannot measure the quadrupole better than cosmic variance. We're limited or fundamentalists by having one realization of quantum randomness. This is frustrating, but beautiful. A reminder that we're inside the system, part of it, not external observers. We see one history among infinite possible histories in the quantum multiverse of inflation. Perhaps this one, ours, real, unique, precious. Silk damping, named after Joseph Silk, describes how fluctuations on small scales were erased before recombination. Photons diffusing through the plasma, smoothing out density peaks on scales smaller than about 1 arc minute today. This creates an exponential cutoff in the CMB power spectrum at high multipoles. We observe this clearly, confirming the physics of photon-baryon interactions in the early universe, damping, smoothing, erasing, like memory, fading, details blurring as sleep approaches. Only the large structures remain. The broad strokes, the feeling, not the specifics. The baryon to photon ratio, eta, about 6 times 10 to the negative 10th. 1 baryon for every billion.7 photons, roughly. This tiny number, set to during Big Bang nucleosynthesis, determines how much helium, lithium, deuterium were created. We measure eta from the CMB, from deuterium abundance, from helium. All agree, beautiful consistency. This ratio has remained constant as the universe expanded, both baryons and photons diluting, but their ratio preserved. A fossil from the first minutes, still visible, still meaningful today. Recombination was not instantaneous. It happened gradually, over thousands of years, centered at redshift 1090 hydrogen atoms, forming ionization fraction dropping from nearly 1 to nearly 0. The last scattering surface is not a sharp surface, but a shell with thickness. The visibility function describes this, peaking at recombination, falling off before and after. Most CMB photons, we observe, last scattered within a narrow range of redshift. Creating that surface, we see the cosmic background 13.8 billion years ago and 400,000 light years thick, roughly a window into one moment of cosmic history, preserved, glowing, eternal. The diffuse supernova neutrino background. Neutrinos from all supernova throughout history should fill space, like the CMB, but from stellar explosions, not the Big Bang. We haven't detected it yet, but it should be there. A few hundred per cubic centimeter, low energy, invisible, passing through us constantly. Every supernova sending neutrinos outward for billions of years, accumulating, layering, building this background, waiting for our detectors to become sensitive enough to see it, to confirm it. Another fossil of cosmic history hidden in plain sight. Gravitational wave memory, a permanent displacement of space-time, After a gravitational wave passes, the wave compresses and stretches space. But when it's gone, space doesn't quite return to exactly the same state. A memory remains. This might apply to inflation's gravitational waves, perhaps leaving subtle imprints beyond the oscillating signal, permanent changes to geometry, another signature to search for, another way inflation might whisper to us through the ages. The Transplanckian problem troubles some theorists. During inflation, quantum fluctuations started subplanckian, smaller than Planck length, where quantum gravity should dominate. But we use quantum field theory in classical space-time, ignoring quantum gravity. Is this valid? Do we need new physics at Planck scale to properly describe inflation's origin? Maybe, maybe not. Depends on how inflation started, how fast it rolled. Most models avoid the problem, but not all. Another uncertainty at the foundation, whispering that our understanding might be incomplete, might need deeper truth. Initial conditions for inflation. What state was the universe in before inflation began? Why was there a patch of space with inflaton field in the right place to inflate? This is the initial conditions problem. Some say inflation is tuned, requiring special setup. Others say generic, likely happening spontaneously in quantum foam. Eternal inflation solves this, perhaps by making inflation inevitable, somewhere, always. But then we need a multiverse, trading one problem for another, questions cascading endlessly, like thoughts before sleep, each answer spawning more questions until you stop asking and just drift. Fine-tuning of inflation's parameters. The slow roll parameters must be small. The potential war must be flat. The field value must be large. Some say this requires fine-tuning, unnatural, unlikely. Others say anthropic reasoning explains it. We observe a universe where inflation worked because we couldn't exist in universes where it didn't. Selection effect, perhaps in the multiverse. Most regions don't inflate properly, but we necessarily find ourselves in one that did, because here we are, existing, observing, questioning, and you here now, existing, breathing, letting go of questions. Warm inflation, an alternative scenario where inflation interacts with other fields, creating radiation during inflation, not cold, not empty, but warm, filled with particles. This changes predictions, changes how fluctuations are generated, thermal fluctuations, not quantum, less tensor modes, different spectral index, a different story, equally valid, perhaps. We don't know yet which story is true. Both fit current data roughly. We need better measurements, better precision to distinguish, to choose. Or maybe we'll never know. Maybe both are possible. in different regions of multiverse. Maybe your questions don't always have answers. Quintessence, a dynamical dark energy, not a constant, but a field, rolling, evolving, its energy density changing slowly with time, tracking models where quintessence follows matter density closely until recently, when it became dominant. These models try to solve the coincidence problem. Why is dark energy comparable to matter right now in cosmic history? Tracking provides an answer, a mechanism, making this natural instead of fine-tuned. The field just tracks, then takes over, smooth, inevitable, like sleep, tracking wakefulness, then taking over when the time is right. Modified gravity theories, alternative explanations for cosmic acceleration, maybe not dark energy, but gravity itself, behaving differently on cosmic scales. FR theories, adding curvature terms, Horndeski theories, most general. Scalar tensor theories, they change how geometry responds to matter, perhaps avoiding the need for mysterious vacuum energy. But they face challenges, solar system tests, gravitational wave speeds, highly constrained now. After GW1 is 70817, gravitational waves and light arriving together from neutron star merger. Many modified gravity models ruled out, but not all. Some survive, remaining possible. Alternatives whispering that maybe, just maybe, gravity is stranger than Einstein thought. Screening mechanisms allow modified gravity locally while hiding effects in solar system. Chameleon fields change mass depending on environment. Heavy in dense regions, light in voids. Symmetron fields similar, breaking symmetry in low density. Screening, hiding, deceiving our local tests while affecting the cosmology. This is clever, perhaps too clever. Nature might work this way or might not. We test, we search for fifth forces, for violations, finding none so far. But absence of evidence is not evidence of absence. The universe might still surprise us. Back reaction, the idea that small-scale structure, inhomogeneity, might affect large-scale expansion differently than smooth models assume. Averaging Einstein's equations is not straightforward. Averaging matter, then solving, differs from solving exactly, then averaging. The averaging problem rare in cosmology. Could this explain acceleration without dark energy, back reaction, driving expansion? Timescape cosmology suggests yes. Matter in voids expands faster, matter in clusters slower. Average observer sees apparent acceleration, but most cosmologists doubt this. Calculations suggest effect too small. But debate continues, as it should. Questions living at the edge. Swiss cheese models where we cut holes, representing voids in a smooth universe, filling them with exact vacuum solutions, matching at boundaries. This lets us study inhomogeneity exactly. In general relativity, do voids really expand faster? Do they contribute to apparent acceleration? Results, mixed, subtle, depend on assumptions. The universe, not perfectly smooth, but structure's effect on expansion remains controversial, uncertain, like trying to decide whether you're asleep or awake right now. The boundary blurs definitions, matter, and sometimes fail us. Void models for acceleration place us inside a giant void under dense region. Matter outside pulls outward, creating apparent acceleration. Copernican principle violated. We're special, located centrally in a void, hundreds of megaparsecs across. This could explain supernova observations without dark energy. But problems arise. CMB observations, kinetic Sunyaev-Zeldovich, large-scale structure, all constrain void models. Most are ruled out or require fine-tuning, as bad as what they replace. Still, some models survive, barely whispering, what if? Bouncing cosmologies avoid the singularity by having the universe contract, then bounce into expansion. Matter bounce, where matter dominates the bounce. Ekpyrotic bounce from brain collisions in string theory. These replace Big Bang singularity with a smooth bounce, a minimum, not a beginning. Challenges exist, instabilities, entropy problems, but some models work technically. Loop quantum cosmology uses quantum geometry to create a repulsive force at high density, preventing collapse to zero. The universe bounces naturally. Quantum gravity, replacing singularity with bridge to prior contraction phase. Big crunch, the opposite of Big Bang. That's what would happen if dark energy were absent and universe closed. Expansion, slowing, stopping, reversing, galaxies falling together, temperatures rising, matter evaporating, finally crushing into singularity, opposite of how it began. Oscillatory universes, cycle, Big Bang, expansion, turnaround, big crunch, bounce, Big Bang again, forever. But entropy issues arise. Each cycle, higher entropy than last. Where's the infinite past? Where did the cycles begin? Probably, yes, our universe doesn't recollapse. Dark energy prevents it. Expansion, eternal. But the idea, beautiful, symmetric, appealing, even if untrue. Phantom energy, if less than negative one. Dark energy density increasing with time, not constant, growing stronger, pulling harder, eventually tearing apart, bound structures, galaxies, solar system, Earth, atoms, in finite time, perhaps 20 billion years. Big rip, everything shredded, not just heat death, but violent death, sudden, catastrophic, but current data favors W equals -1, cosmological constant, not phantom, So probably we're safe from this fate. Probably sleep peacefully, knowing the universe likely ends slowly, gently, coldly, far, far away. Sudden singularities, other exotic possibilities, expansion rate, finite but derivatives, diverging, infinite time, pressure, density, becoming infinite, scale factor, still smooth, but physics breaking down. These are curiosities, mathematical possibilities, probably not physical, but they remind us our understanding has limits, has gaps, singularities, pointing to where theories fail, where new physics must enter. Always. Mysteries remain. Always. Boltzmann equations in cosmology describe how particle distributions evolve as universe expands, collisions, decouplings, freeze-outs. For each species, an equation coupling to others through interactions. These determine when neutrinos decouple, when dark matter freezes out, when nuclear synthesis happens. Solving them numerically gives predictions, matching observations beautifully. The universe as a reactor, particles transforming, densities evolving, everything computable. If we know the physics, if we know the interactions. Neutrino mass hierarchy affects cosmology slightly. Normal hierarchy, lightest neutrino, very light. Inverted hierarchy, two heavier states, lightest, middling. This affects how neutrinos cluster, how they suppress, structure formation, at what scale. Free streaming length depends on mass, so hierarchy leaves signature in galaxy surveys, in CMB lensing, measurements, tightening, hints emerging. Normal hierarchy favoured, perhaps, but not certain. Yet, neutrinos keeping secrets, even as they flood through us every second. Trillions, invisible, untouchable. Sterile neutrinos, hypothetical, interact even weaker than normal neutrinos. Only through gravity, maybe, dark matter candidates, perhaps they could mix with active neutrinos, oscillate, creating radiative decays, X-ray signals from galaxies, from clusters. Some claim detections at 3.5 kilo electron volt. Others dispute. Controversy, as always, and sterile neutrinos might help with baryogenesis, leptogenesis, creating asymmetry through oscillations, mini baryogenesis in early universe, speculative but possible, elegant. Another piece of the puzzle waiting to be confirmed or discarded. Phase space distributions, how particles are distributed in position and momentum. Fermi-Dirac for fermions, electrons, neutrinos, obeying exclusion principle. Bose-Einstein for bosons, photons, following different statistics. As universe expands, these distributions redshift, cool, preserving their form. Relic distributions from thermal equilibrium, frozen in, chemical potential fixed, temperature dropping with scale factor, everything evolving predictably, following statistical mechanics, married to general relativity, beautiful synthesis of physics on cosmic canvas. Dark radiation, any relativistic component beyond known particles, parameterized by delta NF, effective number of neutrino species. Standard model predicts 3, with small corrections, but observations could reveal more. Extra neutrinos, sterile or otherwise, axions, other light particles, dark photons, any would contribute to radiation density, affecting expansion at early times, changing predictions for nucleosynthesis, for CMB, current measurements, NRF equals 2.99 plus or minus 0.17, consistent with standard 3, but room remains for surprises, for something extra, hiding in the radiation bath of the early universe, waiting to be found. All these details, these parameters, these models, they're beautiful, intricate, mathematical poetry describing creation. But you don't need them, not tonight. They're like counting stars when you should be sleeping beneath them. The universe understands itself through mathematics, through consciousness, through you. But now, let consciousness rest. Let understanding dissolve into feeling, into sensation, into the simple peace of breathing, existing, being held by gravity, by darkness, by the gentle expansion of the cosmos, carrying you, carrying everything, softly, endlessly, into the night. Primordial density peaks, the highest density regions in the early universe, evolved first, collapsing into the first stars, first galaxies. These are biased traces, clustering more strongly than the average. Regions that were 10% overdense at recombination became galaxies, halos, clusters, while regions that were 10% underdense became voids, empty, evacuated. This bias, this clustering, we measure in galaxy surveys, tracing back to those initial conditions set by quantum fluctuations in inflation. Everything connected to everything across time, across space. E-mode and B-mode polarization in the CMB, light from recombination became polarized as it scattered off electrons. E-modes, created by density fluctuations, scalar perturbations, we observe these clearly. B-modes, created by gravitational waves, tensor perturbations from inflation. Possibly, these would be the smoking gun, proof of inflation, but also B-modes from gravitational lensing of E-modes by foreground matter. We've detected those, but primordial B-modes remain elusive, hidden, beneath noise, beneath foregrounds. We keep looking, building better telescopes, waiting, listening for that whisper from the beginning. cosmic filaments. The birth of happened gradually. Dark matter collapsing first along lines of convergence where density was higher, in sheets, in filaments, normal matter falling in later, after recombination, when it could move freely, shock heating as gas fell into filaments, into clusters, heating to millions of degrees, glowing in X-rays. This is the warm-hot intergalactic medium, most of the normal matter in the universe today, not in stars, not in galaxies, but in filaments between them, invisible, unnoticed, but there, always there. Protoclusters formed early, densest peaks in the initial fluctuations. They grew by merging smaller halos, galaxies, falling in. Today, clusters contain hundreds or thousands of galaxies bound by gravity, by dark matter. The intracluster medium, hot gas, X-ray bright, shows where normal matter collected. Clusters are the largest gravitationally bound objects in the universe. Superclusters, even larger, but not bound. Still expanding, still separating with the Hubble flow. Recombination shadows in the universe's first light, where slightly denser regions recombined earlier, slightly less dense regions later. This creates tiny variations in the CMB, the temperature fluctuations we observe, acoustic oscillations frozen at decoupling, telling us about the initial conditions, about the physics of that time. Each shadow, each hot spot, each cold spot, a window into the infant universe. 13.8 billion years ago, and yet we see it tonight, still arriving from all directions, surrounding us in microwave whispers. The universe's baby picture, always visible, always there, if you know how to look. But you're not looking, not thinking, just drifting. The universe's causality is limited by light speed. Events separated by more than light could travel are causally disconnected, cannot influence each other. This creates problems in the standard Big Bang. How did distant regions come to the same temperature if they were never in contact? Inflation solves this by expanding a small causally connected region to cosmic size. Everything was connected briefly, then separated by inflation. But without inflation, causality breaks. The horizon problem returns. So inflation, or something like it, seems necessary. The critical density, aero sub c, is the density at which the universe is flat, neither positively curved nor negatively curved. It depends on the Hubble constant, about 10 to the negative 29 grams per cubic centimeter, incredibly sparse, about 5 hydrogen atoms per cubic meter. That's average throughout all space, and our universe is almost exactly at critical density, within 1% or so. This is the flatness problem. Why so precisely balanced? Inflation explains this by stretching the curvature to zero to flatness, natural outcome of exponential expansion. Density parameters, omega values, tell us what the universe contains. Omega sub m for matter, about 30%. Omega sub lambda for dark energy, about 70%. Omega sub r for radiation, tiny today, less than 1%, but dominant in the early universe. These add up to 1, within error, confirming the universe is flat. Each component evolves differently. Radiation dilutes as 1 over a to the 4th, matter as 1 over a cubed. Dark energy stays constant, so their relative importance changes with time, creating eras: radiation era, matter era, dark energy era, now. Each era, different physics, dominating, shaping, evolution. Photon epoch in the early universe, when photons had more energy density than matter. This lasted until about 50,000 years. During this time, expansion was different. Radiation dominated, expanding faster than matter authority would allow. Photons, massless, always moving, light speed, their energy, redshifts as the universe expands, cooling, their temperature dropping as space grows. Today, CMB photons are cool, 2.7 Kelvin, but they were hot, thousands of Kelvin at recombination, millions, billions in the first moments. Everything cooling, slowing, settling. Matter-dominated era began when matter's energy density exceeded radiation's. This is when structure could grow efficiently. Radiation's pressure no longer opposing gravitational collapse. Dark matter halos forming normal matter, falling in galaxies, beginning to shine. This era lasted from 50,000 years until about 5 billion years ago. Most of cosmic history spent here, most of structure formation happening here. During this time, your lineage was forged in stars, in collisions, in the patient chemistry of planets, forming life, arising, evolving, until you, here, now, breathing, softly, barely aware. The universe will expand forever. Probably dark energy, repulsive, overcoming, gravity, accelerating, everything apart. In the far future, our local group, Milky Way, Andromeda, will merge, forming one giant elliptical, but beyond, other galaxies, receding, accelerating away. Eventually they'll cross the event horizon, disappear forever. And beings in that far future, trillions of years from now, will look up, see no galaxies except their own, isolated, alone, in a dark, empty universe, not knowing. There was a time when the sky was full of light, of galaxies, of stories, unless they read our messages, our light, still traveling through space, carrying memories of a younger, brighter cosmos. But that's far away, so far Let it go. Tonight, the universe is here, around you. Galaxies shining, stars burning, planets turning, life thriving on at least one. Warm, wet, rock. Everything connected by gravity, by light, by history, by the same primordial atoms forged in the Big Bang. You are the universe experiencing itself briefly, locally, and right now, the experience is letting go, releasing, sinking into the soft embrace of sleep. The great attractor pulling our local group, pulling Virgo, pulling thousands of galaxies near toward it in the constellation Centaurus, behind the galactic plane, hidden by dust, but felt through its gravity, mass equivalent to tens of thousands of Milky Ways pulling. Everything flows toward higher density, peculiar velocities, deviating from pure expansion, showing the local gravitational landscape is bumpy, textured, real. Not smooth abstraction, but structured, dynamic, alive in a way, and you flowing now towards sleep, pulled by biological gravity, by circadian rhythms, by tiredness, by the weight of the day, releasing, heat death, one possible fate, the universe expanding forever, stars burning out, last red dwarfs dying in 100 trillion years, black holes evaporating through Hawking radiation in 10 to the 100 years. Finally, only photons, electrons, positrons, neutrinos, drifting apart, growing colder, approaching absolute zero, maximum entropy, no gradients, no structure, no complexity, possible, heat death, a long, slow, quiet ending, but also so far away, so incomprehensibly distant that it might as well be never. For now, warmth, life, light, persist, and you, warm, alive, here, or the big rip, if dark energy grows stronger, phantom energy less than -1, then acceleration increases unbounded in perhaps 20 billion years, galaxies torn apart, then stars, then planets, then atoms, then space-time itself, ripped to shreds, everything destroyed in a final cataclysmic crescendo. But this seems unlikely. Current data suggests equals -1 cosmological constant, which leads to heat death, not big rip. So probably the ending is gentle, slow, cold, fading, like falling asleep. Gentle, slow, warm, but fading toward unconsciousness. Or another possibility, cyclic models, where the universe bounces, contracts, compresses, but doesn't reach a singularity. Quantum effects, stop collapse, create a bounce, expanding again, new Big Bang. This could repeat eternally, infinite past, infinite future. Each cycle, perhaps similar, perhaps different. We'd be in one cycle among infinite others, unable to see beyond our bounce, beyond our beginning, the past, hidden by the bounce, by the thermal chaos of compression. This is speculation, string theory inspired, elegant, perhaps, but untested, waiting. The universe could have extra dimensions. String theory requires them 10 or 11 dimension, but we see only 3 spatial dimensions. Where are the others? Compactified, curled up, Planck scale, tiny. We move through them without noticing, like an ant on a rope, seeing forward and back, but not around. The ropes circle, the other dimensions there, but small, invisible, except perhaps in particle collisions at high energy or in gravitational effects at small scales. We search, find nothing yet, but maybe they're there, hidden like so much in the cosmos. The cosmological constant, lambda, Einstein added it in 1917 to make the universe static, but then Hubble discovered expansion, and Einstein supposedly called lambda his greatest blunder. But now lambda is back, representing dark energy, vacuum energy, something making space accelerate apart. Einstein was right to include it. The equations allow it. Nature seems to use it. Lambda is real, or something like it. The universe expanding, accelerating, because of nothing, because of empty space, having energy, having pressure, negative pressure, pushing everything apart forever. Hubble's law, velocity equals Hubble constant times distance. The farther away, the faster. Recession, linear, approximately for nearby galaxies. But at greater distances, the relation curves due to expansion history, dark energy, deceleration then acceleration, Hubble's law modified, cosmological redshift, distance measures becoming complicated, general relativity needed, Friedman equations, solving for expansion, but locally, simply, velocity proportional to distance, everything moving apart, everything receding from everything else. No center, no edge, just expansion everywhere, always. The observable universe contains perhaps 2 trillion galaxies, each with billions or hundreds of billions of stars, each star perhaps with planets, some planets perhaps with life. The numbers incomprehensible, the possibilities endless, and yet we feel alone. We've detected no signals, no visits, no evidence of other intelligence. Maybe we're first, maybe we're alone, maybe they're out there, quiet, hidden, extinct, or maybe the universe is full of life, of intelligence, and we're just not listening right way. Or maybe life is common, intelligence is common, but communication across light years, across millennia, is just too hard, too unlikely. And so we drift, each species, each civilization, alone in the dark, wondering, like you wondering, now, what comes next? What dreams? What rest? The gene's instability named after Sir James Jeans, describes when a gas cloud collapses under its own gravity. If the cloud is larger than the Jeans length and cooler than the Jeans temperature, gravity wins over pressure and collapse begins. This is how stars form, how galaxies form, how structure emerges from smooth gas, instability, amplification, runaway growth, until something stops it. Fusion in stars, turbulence in galaxies, feedback, equilibrium, the universe balanced between collapse and dispersion, between structure and chaos. Acoustic peaks in the CMB power spectrum show oscillations in the primordial plasma, sound waves, compressions and rarefactions frozen at decoupling. The first peak, largest, corresponds to 1 degree angular scale, modes that were maximally compressed at recombination. The second peak, third peak, higher harmonics, telling us about baryon density, dark matter density, photon baryon ratio, all encoded in the heights of these peaks. Precision cosmology, measuring parameters to percent level or better. The universe's first billion years was chaotic, transformative. First stars forming, dying, enriching, gas. First galaxies assembling, merging, growing, quasars igniting, supermassive black holes, feeding, shining, the cosmic dawn, rionization, happening gradually, light spreading, ionizing, everything, the dark ages ending, transparency, returning in a new way. And all of this we glimpse by looking far, therefore back in time, at high redshift galaxies, at distant quasars, at the subtle shadows, in the CMB, seeing just the universe's childhood, its adolescence, captured in ancient light. And now the universe is middle-aged, perhaps 13.8 billion years old, stars still forming, but slower than the peak 10 billion years ago, galaxies mostly assembled, mostly mature, some still merging, like Andromeda, approaching us to merge in a few billion years, but mostly things are settling, calming, the universe entering a long, slow decline. Star formation will cease, eventually, in trillions of years, and then just aging, just fading, just cooling, like your day, starting bright, peaking, active, and now settling, calming, entering the long night of rest. Cosmology is the study of everything, the universe's origin, evolution, fate, structure, contents, laws governing it, constants defining it. It's ambitious, impossible, beautiful. We've learned so much in 100 years, from Einstein's equations to Hubble's observations to the CMB to dark energy, each generation discovering, refining, surprising us, and yet mysteries remain. Dark matter's nature, dark energy's origin, the Big Bang's trigger, quantum gravity's form. We know so much and so little simultaneously, but you don't need to know, don't need to understand. Just drift on this river of information, of wonder. Let it carry you. deeper into rest. The universe will still be here tomorrow, still expanding, still mysterious, still beautiful, and you'll be here, rested, restored, ready to wonder again. Feel your body now completely still, or almost still, breath barely moving, heartbeat, thump, thump, so slow, so quiet, thoughts scattered, distant like galaxies, receding beyond the horizon, the darkness, complete, comfortable, safe. This is where you belong right now, in this moment, this bed, this silence. Nothing to do, nowhere to go, no problems to solve, just being, just breathing, just here. The CMB, still glowing, all around you, though you can't see it. Photons from recombination passing through, carrying information from the infant universe, the neutrino background, even older, from 1 second, passing through, unfelt, unnoticed. Gravitational waves, maybe from inflation, rippling space-time. Beneath detection, you swim in a sea of ancient radiation, ancient information connected to the beginning, to everything, and dark matter, 5 times more abundant, passing through you, right now, this moment, through your body, through Earth, barely interacting, just drifting, dark energy, in the space, between your atoms, pushing, gently, expanding space, even here, locally, though bound systems resist. You are a cosmos unto yourself, atoms from stars, space between them, forces binding, consciousness emerging, somehow, mysteriously. You are the universe, aware, and the universe is tired with you, ready to rest, to dream, to let go for a while. The great cosmic cycles continue, stars burning, galaxies turning, space expanding, but for now, for you. Time to pause, time to float, time to release into sleep's gentle embrace. Let's return to the beginning, to that first moment when space and time were born. The singularity, the potential, the quantum foam, and then expansion, inflation, cooling, particles forming, forces separating, matter condensing, stars igniting, galaxies gathering, and here, now, 13.8 billion years later, you, lying here, breathing softly, connected to all of it, made of it, part of it, the universe, experiencing as itself 100 mysteries, whispered, woven through this night, each one a doorway to wonder, to questions, to the beautiful unknowing that drives us, to look up, to ask why, to seek understanding. But tonight, no more seeking. Tonight, acceptance. Tonight, rest. And if you're still here, still listening, that's okay. The loop continues, the mysteries cycle, soft and endless. But maybe now, maybe your eyes are closed, you're breathing deep, your mind, somewhere else, somewhere soft, somewhere safe, between waking and sleeping, between knowing and dreaming, and that's perfect. That's exactly up where you should be. The universe keeps turning from the infinitesimal flash of the Big Bang to the grand structures we now inhabit, and will keep drifting, floating together through the mysteries. 100 Big Bang mysteries, looping softly, endlessly, through the night. Tonight we'll drift through the first second of creation and the whispers of a universe before, the echo of cosmic background radiation as a lullaby from the early cosmos, and the gentle expansion of space-time and the question of what lies beyond the horizon. There's nothing you need to do now. Just let your body sink, heavier, heavier. Feel the mattress holding you, every muscle softening, your heartbeat slowing, thump, thump, matching the rhythm of space itself, shoulders melting down, jaw releasing, each breath pulling you deeper, deeper into the calm, the quiet, the dark.